Hello everyone, I'm Siddharthan. This is the 8th deep learning project video in my channel, and in this video let's understand how we can build a neural network using PyTorch in Python. And for this purpose we will be using the breast cancer dataset where we will be building a classification neural network using PyTorch. So we have already worked on this breast cancer dataset with machine learning models as well as neural network with TensorFlow. But the main objective of this particular video is not this particular use case itself, but how we can do this in PyTorch. So that will be the agenda for today's video, and let's get started. And before going into the coding aspects, I just wanted to quickly discuss about the different frameworks that we kind of use for deep learning. So we have already worked on TensorFlow and Keras, right? So TensorFlow is, again, we know that it's developed by Google, and the other famous deep learning framework is PyTorch. And PyTorch is developed by Facebook's AI research team. So initially, TensorFlow used to work on this concept of static computational graphs, where we kind of declare all the computational operations that should happen and all the variables and so on. So this is what we call as a statistic, basically a static way of doing things. And then we have this PyTorch where all these computational graphs are built dynamically on the fly, right? So later what happened is, like, this seemed to be a better approach, and from TensorFlow 2.0 version they have kind of included that version as well. But again, both of these are widely used. People kind of always say that PyTorch will be a bit easier compared to TensorFlow. And then we have this Keras, which is kind of a wrapper of this TensorFlow and few other libraries like Microsoft's deep learning framework. So Keras kind of gives this eye-level APIs that you can use in order to build this neural networks, but the problem is you can't kind of build this custom training loops when you want to build like a more complex neural network architecture. So that's where the limitation of Keras comes. But again, it's super beginner friendly and so on. So if you're just starting with deep learning, Keras would be good, but at a particular point you have to kind of learn either TensorFlow or PyTorch. But again, I would tell you, like, not to just say that I know only TensorFlow or I know only PyTorch. So it's always better to kind of stick to one library, but also make sure that you have a good understanding and like practical skill of the other library as well. So that's the agenda, and that's why I wanted to make this video on PyTorch as well. And in my channel I maybe try to make videos on both TensorFlow and PyTorch wherever possible. So that being said, now let's get into the hands-on part where we can try to build this neural network for this breast cancer classification problem. Okay, so I have my Google Collaboratory open, and the first thing to do here is make sure that you are connected to a GPU runtime so that your training is kind of happening faster. This is a small data set. This is like a numerical data set, so this won't take a lot of time. But if you are working with an image classification problem, then you really want to connect to your GPU so that we could accelerate the training. So in your collab, go to your runtime and change runtime type, and you can choose a GPU. So we have this runtime type as Python, and I'm going to choose the hardware accelerator as T4 GPU and save this, and you can connect your system. So now we would be allocated a GPU session. So now let's get into this coding part. So the first step is I'm creating a text cell, and I'll call this as importing the dependencies. Okay, so here let's import all the required dependencies. So let's start with PyTorch. So PyTorch, it's not imported as PyTorch but just as torch. So I'm importing torch, and then I'm importing this torch.nn as nn. Okay, so from this torch we are importing this class called as nn, which stands for neural network. So we will be using this, and then I'm going to import torch.optim as optim. So this is basically used to load our optimizer. So we have this Adam optimizer, stochastic gradient descent, and so on, right? So we would have used this in TensorFlow in model.compile, and here we kind of use this from torch.optim. And then for dataset, I'm going to use the dataset from sklearn library, the breast cancer dataset. So I'll say from sklearn.datasets import load breast cancer. The next thing is, so let's keep the data processing and all this like things simple. So the main focus is to build this neural network. So I'm not going to do a lot of EDA and stuff like that. So let's just keep things simple. So here I'll import from sklearn dot model selection I'm going to import my train testlet. The next thing is, let's also standardize our data. So for that we need from sklearn.preprocessing import standard scalar. Let's run this. Okay, so these are all the required dependencies and the functions. So the next step is we need to kind of configure our device, whether it's going to run on CPU or a GPU. So in TensorFlow, it automatically picks that up. So if you have a GPU, it's going to use it. But for PyTorch, we kind of need to explicitly mention that. So here I'll create this text cell and I'll name this as device configuration. And here we need to say that you can use CUDA. So here I'll put a command saying like check for CUDA. So check for CUDA availability. So here I'm going to say device is equal to torch.device, and here we need to set it up with either CUDA or with CPU, right? So these are like the two options, and basically CUDA is the one that's, this is like a parallel processing architecture that's developed by NVIDIA's, and it's work well with NVIDIA GPUs, and the ones that we connect here are also like NVIDIA GPUs. And what I'm trying to do here is let PyTorch know that you can use this CUDA architecture so that you can do the parallel computing wherever required if GPU is available. So I'm going to say CUDA if torch dot CUDA dot is available. So this basically, so we have this torch.CUDA is available, right? So this basically checks if you have a GPU and that supports CUDA. If that's the case, this is going to turn out as true, and in that case we are going to use CUDA. If we don't have a CUDA enabled GPU, in that case I'm going to say else CPU, right? So the device would be CPU. So if there is an NVIDIA GPU where you can use this, I'm going to go with CUDA. If not, it's going to be a CPU thing. And we can also print and make sure that we have this CUDA now. So here I can say if using device, and here we can substitute this device thing to basically you can run this and check if it's able to access your GPU. So this should say CUDA, so that means like it kind of found this GPU that's available for us over here, this 15 GB GPU thing, and yeah, we can kind of go with the other steps. So the next step is like simple data curation and the pre-processing steps. So I'll call this as a data collection and pre-processing. So as I said, we won't be doing like regressive data pre-processing and analysis here. So we will just like split the data into training set and test set, and we will apply our standard scalar. So here I'll say load the breast cancer data set, and let's call this as data. So data is equal to load the same one that we have imported from sklearn. So call this and say x is equal to data.data. So this data.data contains all the features, and your y contains the target. So data.target. So if you want, you can also train it with a CSV file of this breast cancer data instead of this sklearn, so that you can use it for some other data set. So you can definitely try that, but for easier usage I'm just going with this particular version. So let's run this. So your x should contain your data and y should contain the labels. Maybe we can just try printing this x and y and check. So we have all the features, and then I can print my y. So y contains like all this labels. So maybe one is for benign and the another one is for malignant case. So that's like the two classes that we have, and then we can split. Maybe I'll try printing only like 5 rows, okay, for this label. So as you can see, so now let's split the data set into training and test set. Here let's say x train comma x test, y train comma y test. So these are the two things that we have. So we have a training data in xtrain and the corresponding labels will be stored in ytrain, and then we have the test data features in xtest and the labels for test data is getting stored in ytest. So this is equal to train test split, and within that we can give this x and y. So we have this uppercase x and lowercase y, the usual way of representing this. I'll say x comma y, and let's say the test size is going to be 0.2 and my 20% and my random state is equal to 42. Let's run this, and you can also print and check the shape of this x and y. So we have this xtrain dot shape, and copy this and print this. Let's first maybe print x shape, and then we can try printing xtrain and xtest shape. So your x is like the complete data set, xtrain is your training, and xtest is your test data set. So we can see, so in total you have 569 data points. So 80% of that, which is 455, goes to your training data and 114 goes to your test data on which we will do our evaluation. So the next step is standardizing our data. So for this we can do this like after splitting our data into training and test data to make sure that we don't face any data leakage issues. So here I'm going to say standardize the data using standard scaler. Again, this is used in order to make sure that your data is kind of normally distributed. So if your data is normally distributed, your mean is going to be 0 and your standard deviation is going to be 1. So in order to test this out, what you can do is put this through a distribution plot. So put your training data through a distribution plot and see like what's your distribution plot is for the different columns or the different features. And once you do your standardization, and then you can check it again, and later now you will see a normally distributed curve. So previously you won't be having a normal distribution. So again, the main purpose of doing is like the linear models like logistic regression and SVMs expect the data to be normally distributed. So we kind of have to do that again in neural networks as well. Like it's kind of good to do the standardization, right? And if you're working with mainly tree-based models like random forest and XGBoost, it's kind of not required to do the standardization, but that's the overall idea. So here let's say that this scalar, so I'm creating a variable called a scalar, and this is equal to standard scalar, and then let's scale our data, scale our xtrain and ytrain. So let's say xtrain is equal to scalar dot fit transform xtrain, and then for test data we don't have to do a fit transform, we can just do a transform. So it should be scalar dot transform. Okay, so this is because we always fit our transformer or the scalar on the training data and then transform it. So you shouldn't kind of fit your scalar to the test data. So your test data should be scaled based on the scalar that you got after fitting your training data. So this is how you should do it. So scalar should be fitted and transformed on your xtrain, and it just should be use that scalar to transform your xtest. So we can run this, and now your data will be normally distributed following all those process. And the next step is now it's probably in a numpy array. You can also check the type of xtrain and ytrain. So let me check this type of xtrain, and it says numpy and d array. And now we can't use this numpy array in PyTorch. The preferred data type through which we kind of do this computations in PyTorch is tensors. So we need to convert this numpy array into tensors. So for that we can just we'll write a command saying convert data to PyTorch tensors, and yeah, and the other step that we can do here is move it to GPU. Again, we know that GPU is available, so we are doing it. If not, you can just maybe move it to CPU and try that out. So this is because we want our processing and training should happen in GPU, right? So we kind of move all this data to the GPU's memory. So that's the idea over here. And I'm going to say xtrain is equal to torch, which is the library that we have imported, dot to tensor, sorry, just tensor, and within that I can say xtrain, and we have to mention like the data type as well. So I'm going to mention the type is equal to torch dot floating point. So let's take like 32-bit floating points and say dot to device. So this device is nothing but CUDA, the GPU that we have already kind of loaded right within this variable called as device. So that's what I'm saying. So this will move your training data into GPU after converting it to PyTorch tensor. And we have to do this for the labels as well as the test data. So I'll paste all these things here and we can just uh, you know copy and paste these things here. So first we are moving the training data. So white train also goes here and it moves to the device, and then we do the same thing for test data as well. So we have this x test, and finally do this for your white test. Okay, so basically we are converting our numpy arrays into tensors and then moving it to device. But you probably know what a tensor is, but if you don't know, I'll just like have this picture to explain you. So it's again it's think about this. So scalar is like a single value, right? So it's in this case, in this image it says 11, so it's a single value. And vector, it's kind of like an array. So it's, let's say it has like one dimension, so it has like one row, 5, 3 and 7. And then this is like a column vector, just like the same vector, so no issues with these two. And then we have a matrix which is like a two-dimensional data type. So you have this rows and columns. So in this case we have 2 rows and 3 columns. So this is what a matrix is. But tensor, you can think about it as like multi-dimensional matrix. So if you see this one, right, so it has like, it's kind of has this depth as well. So it's 3 rows and 3 columns, but also it has like 3 other values as well. So this is what we call as tensor. You can just think about it as like an higher dimension of a matrix, right? So that's what a tensor is. So we need to convert all this data into tensor for PyTorch to be able to do this processing. And again, tensor has this advantage of making use of the GPU acceleration, and computation kind of happens faster, and it has all these benefits. But yeah, just understand that we need to do this conversion, but maybe all those details you can look up later, or maybe later I can post a video for that as well. But yeah, that's the overall idea, which is to convert these to PyTorch tensors and move it to the device, in this case which is a GPU, so which we have already loaded here. Now I'll run this. Okay, so the next step that we are going to do is build the neural network architecture. And again, this is the first time that we are building our neural network in PyTorch. So let's keep things simple here. So it's going to be a bit different from what we have done before. So previously we have kind of used Keras with TensorFlow backend. So things were like pretty simple here. Basically simple there. But here it's going to be slightly different. It's not hard, but it's just different. Let's understand that. So here I'll say neural network architecture. Let's make this in bold, and here let's say define the neural network architecture. So again, this is not CNN or something. This is just like a simple artificial neural network. So later maybe we can build a CNN with PyTorch as well. And then here I'm going to create a class called as neural network, or let's say neural net, and within this I'm going to say nn.module. Okay, so this may seem a bit new to you. Maybe before that I'll just add this one thing alone. So diff, we're going to use this init function or init method so that we can initiate few parameters over here. Okay, so let's understand this. So we are creating a class called as neural net, and within this parenthesis we are kind of passing something called as nn.module. So nn is nothing but the torch.neural network that we have imported as nn, and within this nn we have another, let's say, subclass called as module. So when I say class of neural network nn.module, I am inheriting the characteristics of this particular class, the nn.module class, to my class called as neural network. So this is what we call as inheritance, where we kind of inherit let's say the methods and the variables of, not variables, let's say parameters. So we inherit the parameters and the methods of this class to this class called as neural network. So that's what we do. And in the next step we have like all these functions. So first is like init function, where we kind of define all the parameters that the model needs. So within this init, I'm going to say first parameter is going to be self. I hope you know what this self is. So later we will load this neural network into a class, sorry, into a variable. So this is what we call as initiating a class or instantiating a class, and the self is kind of addressing to that. So let's say that later we create a variable called as model is equal to neural net, and within this parenthesis we would pass some values, whatever the values that we are going to give it. So all these basically we have this model is equal to neural net, right? So this model is basically we are giving an instance of this neural net to this, and this model is what we refer as self in this case. So yeah, that's about it. And then we need like some input parameters like the input size, and then we are going to give the return size, and then we need this output size. So input size is basically how many number of neurons should be present in your input layer. So we would have used this layers.flatten in Keras, right, where basically the input layer that contains the same number of neurons as the number of features. So this is that number, like how many features are there in your data set, so that how many neurons should be there in your input layer. And then you have this return size. Return size is how many neurons should be present in your return layer. So that's what this return size means. And then we have this output size, which basically represents the number of neurons in the output layer. So here we are working with a binary classification problem. So let's say that we have two neurons or something. It's usually equal to the number of classes that you have in your data set. In this class, it's going, in this use case data set, it's going to be 2, so your output size is 2. So that's how we can initiate these parameters. Again, you can do this differently. This is just like one way of doing this, right? So next step is I'm going to do another interesting thing calling super neural net comma self dot init. So you might not have seen something like this. So here what we are doing is, as I said, so we are inheriting the components, or let's say the methods and the parameters of this NN module to this neural net, right? So when we call this super, again it does this inheritance. It's kind of like a check. It makes sure that whatever we need from this module class is kind of initiated properly. So all the parameters and stuff are getting initiated properly, and the super is like kind of like a built-in function that we have in Python. So again, it's mainly for inheritance. So inherit all the things that this nn.module needs, so that again it's like a validation check that you need to do. So that's the step we are doing here, super neural net. So I'm kind of inheriting all these things to this class called as neural net, and then we can create our init parameters. So I'll say self dot fc1 is equal to nn dot linear. So I'm taking like a linear layer, and here I'm going to say input size comma return size. So I'll explain you in a minute after writing this piece of code. So what's the purpose of this? And then I'll say self dot relu is equal to nn dot relu. So E should be in lowercase, R, L, and U should be in uppercase. And then let's put a parenthesis here. And now I'm going to say self dot fc2 is equal to nn dot linear hidden size. And then we have this output size self dot sigmoid is equal to nn dot capital S, and then we have this sigmoid. So let's understand this. So in TensorFlow, or basically in Keras, when we build our neural network, we would mention our input layer with this layers thing, right? But in PyTorch, you don't have to do that explicitly. So when you give this input size, that input layer is kind of taken care of. So we have to start with the next layer, which is the hidden layers. So FC basically represents your fully connected layers, or basically your hidden layers, right? So your fully connected layer, and FC1 is your first fully connected layer, and FC2 is your second fully connected layer. So basically I'm having like two fully connected layers here. If you want to add more, you can do that as well. right? So okay, let's maybe first understand this. So I'm calling this self.fc1. So whenever you're initiating these stuff inside this unit, you do this self dot, because again it's referred to that variable that we would later create for this particular class. So we have the self.fc1 is equal to nn dot linear. So we are taking like a linear network where it basically does a linear transformation of the data that it takes in. So here we are passing two parameters. One is input size and hidden size. And this is basically the first input size represents how many neurons should be present in your fully connected layers, and this should correspond to the number of input data that is coming to it. And the second parameter is like what's the output sizes, what's the output or basically the number of neurons in the second layer. Maybe I'll show this to you with a diagram that would make more sense. So let's say that okay, so I can take this one. So we have this input layer, and then we have like 3 hidden layers and 1 output layer, right? So consider that the input layer is already taken care of when we gave the input size, and then we have this, let's call this as the FC1, the fully connected layer 1. Okay, so this is my FC1. So here count the number of inputs that it is getting. It's kind of getting, so we have 1 2 3 4 and 5. So your input size is going to be 5, and hidden size is how many output it should give out. So for that you need to count this one and in this case the hidden size is going to be the same, right, for all the hidden layers. So we can just go with that, but if you want you can also change this number. For let's say a particular hidden layer has a different number and another hidden layer has a different number, you can do that as well. So basically the first parameter takes in like the number of inputs that it's going to get, and the second parameter is like how many output it has to send. So we have this input size coming into it, and output hidden size is like how many values it should pass. So this is for fully connected layers, and here we are going to add like a ReLU activation function so that we can add non-linearity. So in this step it basically does a linear transformation because we have added like a linear layer to it, and this ReLU makes sure that the model has some non-linearity to it so that it can capture those complex relationships in the data. And then we have this FC2, which is let's say the second fully connected layer. So it has this hidden size. This would be the input for this layer, right? So for first layer the output is hidden size, and for FC2 the input is going to be that hidden size. So we have that, and the output is going to be output size, which is 2, because let's say this is kind of our final layer. So we have this output size, and we know that for binary classification we use sigmoid activation that gives you the output between 0 and 1, so just like probability. So recently I've made video on different activation functions and why it is used, so that's for this purpose. Okay, so this is the stuff that we have in init. If you want to add this dropouts and other layers, you can maybe like add it here and work on it, but just to keep things simple I'm just going to use this one for the example. Okay, so the next step is we are going to create another function and call this as forward. So this is basically the forward pass or forward propagation for our neural network. So let's say that forward, and we know that the first parameter is going to be self, and now we are going to pass this x. So x is nothing but we would have this batch size and pass the data as batches, right? So that's what this x represent. So let's say that this out is equal to self dot fc1. So we know that fc1 is your input for fully connected layer 1, and we are going to pass our x here. And now let's say that out is equal to self dot ReLU, and within this we have to pass this out, and then the next out will be self dot fc2, and again we need to pass this out. The next step is out is equal to self dot sigmoid, and finally you return your out. Okay, let's understand that. So what this basically gives you is, so you pass a data to this forward function, and that would process your data through the neural network, or basically your training or evaluation happens and you would get the output. So that's what this function does. And now basically we pass the data through all the layers that we have created here. So we have this x, and first like we have this input layer that's getting created implicitly, and then we are passing our data to the fully connected layer, and this fully connected layer, as I said, it would perform a transformation on the data set. So here it's going to be a linear transformation, right? So we pass this to the fully connected layer, and then we store this output in the variable called as out, and then we pass this out through the relu activation functions to apply the activation functions, right? So relu, basically, if the output value is negative number, it's going to turn it to 0. If it's a positive number, it's going to give whatever number it is. So basically we are passing it through the fully connected layer 1 and then applying the activation function, and all this output are saved in the same variable. So it's this out variable is basically getting replaced with all the outputs, and then we pass this output value to this fully connected layer 2, get the output here, and then apply the sigmoid to the final transformation, the same order that we have over here, and finally you would return your out. So this is the forward propagation, or basically what basically happens when your data or your batch passes through the neural network in the forward propagation. And we know that the another important aspect of the neural network is backward propagation, and that we would kind of build in the part where we would build this training loop for our model. So before that, we kind of need to define some hyperparameters, kind of say like what kind of loss function and optimizers that you need. So let's work on that. So let this part is, let's say, initialize the, or maybe first we have to create the hyperparameters, right? So I'll say this as define hyperparameters, and here the first hyperparameter is input size. Basically not just hyperparameters, but like all the parameters that we would need. So let's say that the input size is going to be the number of features, right? So the number of features is xtrain.shape. It's going to take the value 1. So when I say xtrain.shape, it's nothing but this is my xtrain shape 455, 30. So xtrain.shape of 0 is this value, xtrain.shape of 1 is this value. So I'm going to pass this 30 here. So that's what we are taking, xtrain.shape of 1. And my return size, let's maybe take 64 neurons in this case. You can also take like 32 neurons or 128 neurons, anything of your choice, but I'll just go with this 64. And output size, I'm going to give this as 1. This is because I'm having a sigmoid, so I don't need two neurons, but it's just a single neuron that would give the value between 0 and 1. And if the value is greater than 0.5, I'm going to say that it belongs to class 1, and if it's less than 0.5, I'm going to say it's the value is, I mean the class is 0, right? So it's basically like the output of a logistic regression. So based on that, we would kind of map it to the classes. I'm having like one neuron that would give the value between 0 and 1, and then you can again set some learning rate. So I'm just going with 0. Let's say 001. You can also try with different things, do some hyperparam tuning as well. You can do this maybe manually first, and you can check it out. And let's say number of epochs is equal to 100. So this is like a smaller data set. You can also check with smaller number of epochs to anything of your choice here. So I'll run this. So we have like we have the hyperparameters like learning rate and number of epochs, and then we also have the parameters like the input size, hidden size, output size, and so on. So the next step is we are going to initialize this model. So I'm going to say initialize the neural network, and we also have to move it to the GPU, just like the way we have moved the PyTorch tensors to the GPU. So here I'll say model is equal to neural net, and within this we need to pass the parameters. So the parameters it's going to need are your input size, hidden size, and your output size, right? So we need to pass those as well. So here we say input size comma hidden size, and finally we have our output size. Okay, and then we need to move this to device. So to device, so we are moving this to CUDA, or let's say the GPU, neural net to device. Okay, neural net is not defined. I think oh, I didn't run this cell, that's why. Okay, so we have this one, and then we have to define the loss here. So define loss and the optimizer. So we kind of call this as criterion, again the same loss that we have. So I'll use this term criterion itself, dot BCE loss, which is basically your binary cross entropy loss. And this is the one that we would use in logistic regression as well. So I have to check, I kind of forgot, but yeah, I think that's like uh, the binary cross entropy loss. And then we have the optimizer, right? So let's call this as optimizer, and optimizer is equal to optim. So if you remember, we have imported this torch.optim as optim. So I'm saying that optimizer is equal to optim dot Adam. So we are going to use the Adam optimizer, which is again the widely used one, and the parameters that we are going to pass are the model parameters. These are the steps like where you're creating this and kind of like a step happens to optimize your parameters and your bias and so on. So you have this model parameters, and then you also pass your learning rate as the parameters LR. So these two are enough. Okay, so we have our model dot parameters and learning rate. So basically you have this forward propagation, and in the step of backward propagation all your weights are going to change, right? So that's what will happen here. So we are mentioning this loss and optimizers. In Keras we would do the same thing, defining your loss and optimizer in model.compile step. It's again similar to that one. And the next step is we can now move on to the model training step, where we kind of have this for loop and say like what are all the sequence of steps that should happen. So here this part will be training the neural network, training the neural network. So here I'm going to say we can create a comment here as well, training the model or training the neural network, whatever. So here I'm going to say for epoch in range num epochs. So here we have defined the number of epochs, right? So this one, number of epochs is equal to 100. So again in Keras we use this model dot or sequential dot this thing dot fit, right? But here we need to kind of build a loop for this. So for epoch and range number of epochs is when your entire data set has gone through the model for this forward propagation and backward propagation is what we call as epochs. So for epoch and range of number of epochs, it basically this for loop runs for 100 times, and here I'm going to say model dot train. So this is an interesting step. So model dot train basically kind of puts your model in training mode. So here you can see this help section, right? So whether to set training mode or evaluation mode. So later we will use something called as model.eval. So that would basically put your model in evaluation mode. So the purpose of this is when you are in training mode, the model should learn from the data. So it should optimize your weights, or it should change your weights and bias depending on how it's making the prediction. But it shouldn't do that in evaluation. So in evaluation, you have a trained model and it's going to give you a predicted value, right? So these are the things where these are things why we need to set this. So here we are saying that the model is in training mode, and then you can kind of do your training, learn from it, and optimize your parameters. So here I'm going to say optimizer dot zero grad. So this is an interesting kind of step. So all this kind of happens in Keras and TensorFlow as well, but all these are implicit in Keras. So that's why we call that as a library that gives like high level APIs to train the model. Again, it's easier for beginners, but again, we can't customize it a lot. So that's like the downside of this. So we have this optimizer. I have a spelling mistake here. Okay, so we have this optimizer. So zero grad. So what it does is each time the batch is parsed it's kind of resets the gradients to 0. So if we don't do that, it's kind of do something called as this gradient accumulation takes place. So we kind of reset the gradients like each time of this epoch. So we have this model.train and optimizer.zero grad, and then we have this outputs is equal to model of x-train, and this is where you're basically predicting the values for it. So this is your training data, and when training happens, we know that it passes through the neural network, and our neural network gives out a value, right? And that's what happens in this particular step. So when you call this output is equal to model of x train. So model is your neural network. So it automatically calls this forward function. So that's what basically happens here. So you don't need to explicitly mention calling the forward pass, but that's what happens when you say model of x train. And then you kind of calculate your loss, which is equal to criterion, which is the variable that we have created here. So it should be loss is equal to criterion output. So we know that loss function basically compares your predicted output to your true label and find how distance your predicted value and true labels are here, right? So you need to pass your y true. I think it's y train in this case, dot view. This is again it's a simple reshaping that we need. So the criterion thing expects the model in this particular shape. So we are passing this y train dot view. This is just like a reshaping thing, like nothing complex in this. So we have this loss is equal to criterion, and then the next step is we have this loss dot backward. So this is where your backward propagation happens, and we would kind of change the model parameters. So here I'll say optimizer. We can copy this. So optimizer dot step. Okay, so your updation of your weights and your bias, all those things happen. So this is basically your training step. So we are running this for this many number of epochs, putting the model on training mode, and each step we are kind of zeroing the gradients, and we are getting the prediction for the training data, and then calculating the loss function with the predicted the outputs that we are getting and the y train, and then calculating this loss function here, and then we have this backward propagation step and the optimizer step where it updates the weights and bias. And this is all. So once this is done, you can you have your trained model within this model and you can evaluate it. But if you want to log the performance of the model, you have to write some lines of code in order to print the accuracy as well. So here I'll say calculate. Again, I hope by this point you know like how all these things are automated in Keras, so we don't have to worry about all these things. So it automatically prints the loss and accuracy at the end of each epoch, but we have to kind of do this in PyTorch. So let's say that calculate accuracy with torch.nograd. Again, this is like we just need to find the accuracy. While predicting it, we shouldn't update the weight, so we are not going to have this gradient over here. So that's why we say that with torch.nograd, where it basically, as you can see, so saw this help thing here. So it won't update your weights, or it won't kind of worry about the gradients. So gradients are not updated, so that flag is turned on. So that's what we are doing with this torch.nograd. And within this torch.nograd, I'm going to create this variable called as predicted, which is equal to outputs. So we know that our output is going to be a single value because we have only one neuron, so it's going to give out value between 0 and 1. So here we are getting this predicted is equal to outputs dot round. So a value is greater than 0.5, it would turn that to 1. If it's less than 0.5, it would turn that to 0. You can, let's say you want to increase this threshold to 0.6, you can manually do that as well. So instead of this rounding, you can put a if condition that would do that particular conversion. And then I'll say, so here we need this count of correct predictions. So I'll say a simple step of predicted is equal to y train dot view. Again, we do this reshaping minus 1 comma 1, and then I'm kind of converting this to float dot sum. Basically, in this step I'm counting like how many correct predictions are there. So when I check this predicted is equal to y train view, so again, don't worry about this reshaping. This basically counts whether, like, I mean, how many predicted values are the same as the y train, and then we are kind of finding the sum of it and storing it in correct. So this would give you the number of correct predictions, and then in order to calculate the accuracy, you can say accuracy is equal to correct slash y train size. Y train size is your, I mean, the entire size of the data points. Let's say that you have 100 data points or 115 data points, so you divide the correct prediction by the entire number, you would get the accuracy, right? So that's what we are doing. And then we can, let's say I'm not going to print the accuracy and loss function in each step, so I'm going to print at every 10th epoch. So it will be printed in 10th epoch, 20th epoch, and so on. So if you are, let's say, having 10 epochs total and you want to print it at each epoch, you can rewrite the code in that way as well. So this is basically for logging your performance. So let's say that if epoch plus 1, again this is because your number starts from 0, so I'm putting plus 1 because so that the count here is like from 1 to 3 and all the way up to 10th epoch. That's why it's like a simple thing. So we have epoch plus 1 percentage of 10 is equal to 0. Again, this is not complex, it's just like simple operation where we kind of get the reminder, basically the modulus operator. So we basically we take this number divided by 10 and check if the remainder is 0. If the remainder is 0, that means it's divisible by 10. So it kind of, this condition gets satisfied in 10th epoch, 20th epoch, 30th epoch, and so on. So that's the idea. You don't, I mean, I'm just complicating things, but yeah, that's the idea here. So this if condition would run at every 10th epoch. So in every 10th epoch, I'm going to print these things. So we have epoch number. So epoch, let's say epoch plus 1. Let's put an if. Okay, if is already here. So let's say epoch of epoch plus 1 slash number of epochs. So the number of epochs is basically 100, right? So you will understand like when we are printing it, so don't worry if you are not getting this. And the next one is I need to get the loss. So loss you can get it from this loss dot item. So the loss, the one that we have created here, so you can just say loss dot item, and you can just say like how many decimal points you want. Let's say I want three floating point values, and then we have the accuracy, and this accuracy we need to print it, the one that we have calculated here, right? So accuracy, let's say accuracy dot item, we're going to multiply it with 100 to give the value in percentage, and let's say that we need it in 2 decimal values dot 2f, and finally we can just put a percentage symbol here. This is just like some string concatenation thing, just like a complex way of doing it, where we are basically printing the number of epochs. So 10th epoch would display this as 10 by 100th epoch, and what's the loss function at that point, what's the accuracy at that point. Similarly at 20th epoch, 30th epoch, and so on. So if we run this, we would get the epoch number, loss function value, as well as the accuracy at 10th iteration of this. Let's run this, and this is where the training actually happens. As no attribute sum. Okay, I did something wrong here. So it's float dot sum white train dot view dot float. Okay, I missed the parenthesis here. Okay, let's run this again. We'll initiate this model again. So this is what we kind of built using this square bracket thing. So it says at 10th epoch out of 100th epoch, your loss function value is 0.56 and your accuracy was 87, and it kind of went all the way up to 97.36. So that's what it means, and the loss function value decreased. So this is what we have logged using this print statement. Okay, so this is how we kind of train our model with this 100 epochs, and the last final step is evaluating it. So similar to this training while loop, we can kind of calculate this model's performance as well. So maybe we can evaluate our model on the training data set as well as the test data set. So here I'll create something called as model evaluation, and here we need to pass our, maybe for training data accuracy you can pass your xtrain and ytrain, and for test data you can pass your xtest and ytest. So maybe first I'll evaluation on training set first, so that we can make sure if overfitting, underfitting, all the things are not happening. So the first thing is put your model in evaluation mode. So previously we put it on training mode, right? In evaluation mode, when you pass your data, it's not going to change the gradients or change basically your weights and bias. That's the idea. Here also we have to say with torch.nograd. So here we are not kind of focusing on calculating any gradients, updating them. Gradient, you know, right? So it's used basically to update your weights. So gradient is like how your loss function is going to change when a particular parameter changes. So we don't have to do that when you're finding the accuracy or your evaluations. So that's why we are putting this on no grad. And here I'm going to say outputs. As you know that outputs basically call your output from the model. So I'll say model dot, okay, model exchange. So this would give the value, put this data through the forward pass and give the value. And again, this is getting the prediction out of this. I think I use this same thing over here. So prediction is equal to, I can use this same accuracy and use this over here. Okay, and this is the number of correct prediction. All the things are okay. And train view float. So we have this outputs. Outputs isn't predicted. Okay, so this is cool. Let's run this and check if, I mean, like, what's the accuracy that we are getting. So we have this accuracy score over here, and maybe we can use this thing as well. Yeah, we can use this to convert it to percentage, so no issue. So I'll just say print accuracy on training data. So that is the same thing, accuracy dot item. This thing can be used to just convert it in percentage and add a, okay, put this curly brackets and add a percentage symbol here. So let's maybe run this and check if this is working. Yeah, the accuracy on training set is 97.36, the same value that we got in the last epoch, right? So yeah, it's working. And let's also calculate it for test data. So for test data, you need to convert this X train to X test, and for Y train, here it should be, we have to compare it with Y test, right? So this should also be the case here. So this is to, yeah, count the items. Let's run this and check what's the accuracy on this data. The accuracy on test data is 96.49%. So this is how you kind of take a data set and train your neural network. But the key thing is doing this on PyTorch instead of Keras. So it may seem a bit different because everything was easier in Keras, but again, you have to learn either TensorFlow or PyTorch. It's going to be really helpful when you're kind of building these complex neural networks, so that you have this liberty and freedom to customize the network as you want. So that is the idea for this. Maybe I'll just give you a quick walkthrough of what we have done, just like a quick recap. So first, we are importing all the required dependencies. So these are like the basic standard things. The critical things here are your PyTorch library, NN from this PyTorch thing, and then we also have this optimizers. And here we are configuring our device to use CUDA, and the data collection step, pre-processing, all these usual things that we used to do. And the other interesting step that we did is convert all this NumPy arrays to PyTorch tensors and move that to GPU. And the next part is model architecture, where we are using this inheritance kind of concept, where we inherit the, let's say, parameters and the methods from the CNN.module to the custom class that we are creating called as neural net. So mentioning all the parameters that we need to pass, which is the number of input features or the input size, the number of neurons in the hidden layers, output size, and so on. And then you have a fully connected layer, ReLU, fully connected second, fully connected layer, sigmoid, and so on. And then you have a forward pass, and then you have this hyperparameters. All those are set up here, and then we are creating an instance of this neural net model, compiling our model with the appropriate loss function and the optimizers, and finally we are kind of creating this training loop where it runs for, let's say, 100 epochs in this case, and at each at 10th epoch we are printing this loss, accuracy, and so on. Finally, we are putting our model in evaluation mode and getting the training accuracy and testing accuracy. So that's it from my side, and I hope that you understood all these things completely. So please try this code out and learn from it. So that's it from my side, and I'll see you in the next upload. Thanks for watching.